Welcome to this problem solving session number 6. In this problem solving session, we are going to solve problems related to Jaynes-Cummings model primarily. So problem 1 says you have to work out the full Jaynes-Cummings RWA Hamiltonian in the matrix form. We have done it in the class, but we skip certain steps. Let me now fill up the gaps here. So in lecture number 15 of the course, which is lecture 5 of module 2, we wrote down the Jaynes-Cummings Hamiltonian as follows. H is equal to h cross omega a dagger a plus h cross omega atom sigma z plus 1 by 2 plus h cross z sigma x a plus a dagger. Okay, now under the rotating wave approximation, we wrote this Jaynes-Cummings Hamiltonian as follows. H is equal to first two terms remains unaltered. We have h cross omega a dagger a plus h cross omega atom sigma z plus 1 by 2. However, the last term we wrote as h cross z sigma, that is plus, that is the atomic raising operator, and this annihilation operator a plus sigma minus a dagger. Sigma minus is the atomic lowering operator. Now to express this Hamiltonian in the matrix form, let us make the basis states. Take the basis states as atom in the ground state and n number of atoms, n number of photons in the field, and the other one atom in the excited state, and there is one less photon in the field. Okay, this we are going to take as our basis. To simplify the notation, I will take it as Kate, I will denote it as Kate alpha, and this one I will denote as Kate beta. Alright, now using the fact that h is equal to, we can write it as we have done it so many times. So we have I say h j j. Now because we have only two Kates here, alpha and beta, the Jaynes-Cummings Hamiltonian we can write. Okay, first let me write it, expand this term. We'll have alpha h alpha, Kate alpha bra alpha, sorry, that will be bra alpha. Okay, then we have beta h beta, Kate beta bra beta. Then we have say alpha h beta, then alpha beta, and we will have beta h alpha, Kate beta bra alpha. Okay, so this is what we will have. Let us work out various terms one by one. However, even before that, let me first work out h alpha and h beta. But first let me work out h of alpha. So that would be h alpha, h is h cross omega a dagger a plus h cross omega atom sigma z plus 1 by 2 h cross z sigma plus a plus sigma minus a dagger. All these are operators. And then this Kate alpha is this ground state and field state. So this is what we have. Let me work out the terms separately. Say a dagger a, when it operates on this state, A dagger A is associated with the field mode, so therefore it will act only on the field state, that is your ket n it will act. So because this is a number operator, we will have n and this will remain as it is. Okay, because you know that A dagger A, when it operates on the number operator, you will get, this is the eigenvalue equation, you know. Okay, now what we have, the second term. To work out this term, first let me see what these guys do. Sigma z, you see, when it operates on this atom in the ground state, in fact, you know, this atom in the ground state, we can write it in a, represent it in a column vector as 0 1, this state, and sigma z is the matrix, that is your 1 0 0 minus 1. So if you multiply these two matrices, you will get 0 minus 1, which you can write it as minus 0 1. So this implies that sigma z you can write it as minus 1 when we have the ground state of the atom. Therefore, when H cross omega atom, we have sigma z plus 1 by 2, it operates on this state, you will get, because this would now become minus 1, therefore this whole thing would become equal to 0. On the other hand, you can similarly show that sigma z is equal to plus 1 when we have the atomic state to be in the excited one. Therefore, we can write, if H cross omega atom, if it operates on the other basis, that is your atom in the up state and field is n minus 1, field mode has one less photon, then you will see that because now sigma z is equal to plus 1, so you will have H cross omega atom, and here you will have atom in the up state and n minus 1. Okay, again we can write work out this one, sigma plus a when it operates on this state. Now sigma plus is the atomic raising operator, so it will raise the atomic state to the up one, and a is the annihilation operator of the field mode. It will act on the field mode and it will reduce it by 1, and here the factor, you know, this root over n. Just recall that when an a operates on this number ket, you will get square root of n minus 1. Okay, and when sigma minus a dagger operates on this state, because already the atom is in the ground state, it cannot go lower than that, so therefore sigma minus, which is the atomic lowering operator, it cannot lower it further, so you will get simply 0 here. On the other hand, if you look at the other basis, sigma plus a, when it act on the atom in the excited state and the field mode has n minus 1 number of photons, then sigma plus it cannot, because you have only 2 energy levels only, atomic energy level, already it is in the excited state, it cannot increase it further, it cannot raise it further, so therefore here you will get 0. On the other hand, when sigma minus it a dagger operates on this state, here you will this atomic lowering operator is going to lower the atomic state to ground state, and a dagger, when it applied on n minus 1, it will make it n, and here the factor would be this. Again, you recall that a dagger n, when it acts on, you know that this would be square root of n plus 1, and here n, it would be n plus 1. So we now get all the terms, so we can now work out what is h of alpha. H of alpha is this atomic down state, ground state, and n this is the field mode. So we have worked out all the terms, so let me just write down the results. So you just look at this one here. So we have everything at our disposal, so let me write down the final result. You are going to get h cross omega n down state of the atom, and n here, and here you will have another term h cross z square root of n up state of the atom, and n minus 1. Again you can work out h beta, everything, all the terms we know, so this also you can work out. This would be beta, kate beta is atom in the excited state, and n minus 1 number of photons in the field mode. And here you are going to get h cross omega n minus 1 atom up state, n minus 1 photons in the field mode, and you will have h cross omega atom in the up state, n minus 1 number of atoms in the field mode, and the last term would be h cross z square root of n atom in the down state, and here n number of photons in the field mode. So because now we have this, we have worked out, so we can easily find out all the elements. So alpha h alpha, that is you have to look at the expressions and you can immediately make it out that this would be simply, if you look at this one, you will get, it would be h cross omega n, because you know that these states are normalized. On the other hand, if you have inner product with like this, then you know that this would be equal to 0. So utilizing these relations, you can immediately work out all the terms. Similarly, you have alpha h beta, that would be this one, here it is upstate n minus 1. So again, if you look at this term, you can find out that this would be equal to h cross z square root of n, and beta h alpha, that is beta is atom in the upstate, n minus 1 photons in the field mode, h atom in the ground state, and n number of photons in the field mode. If you work it out, you will again get h cross z square root of n, and finally beta h beta, that would be equal to, so let me write down it explicitly. You will have this one here, so you just have to take the inner product with the state, then you are going to get it as h cross omega n minus 1 plus h cross omega atom. So thus we can write the Hamiltonian in the matrix form as follows. Now we have all the elements at our disposal, so we have this matrix element alpha h alpha, alpha h beta, beta h alpha, and beta h beta. We have evaluated all of them, so if we put them, we will have here h cross omega n, here we will have h cross z square root of n, here we will have h cross z square root of n, and here we have h cross omega n minus 1 plus h cross omega atom. So this is the Jaynes-Cummings Hamiltonian in the matrix form under rotating wave approximation. Now let us work out this particular problem. You are asked to discuss the dress-state picture of the JC model under rotating wave approximation. So let us first of all write down the Jaynes-Cummings Hamiltonian under RWA, which just we have worked out, that is h cross omega n here, h cross z square root of n h cross z square root of n and h cross omega n plus h cross delta. Here the detuning parameter delta is equal to omega atom minus omega. Now earlier we have actually worked out the eigenvalues also in the class. So eigenvalues are two eigenvalues. We have E plus, that would be h cross omega n plus h cross delta by 2 plus h cross square root of z square n plus delta by 2 whole square, and E minus is equal to h cross omega n plus h cross delta by 2 minus h cross z square n plus delta by 2 whole square. Okay, so the eigenstate of this Hamiltonian are the Jaynes-states. So let us denote their eigenstates corresponding to the eigenvalue E plus to be plus ket, and corresponding to E minus the eigenstate is say this ket minus, and these are the Jaynes-state and they satisfy this equation H. If you apply on plus ket, you will get E plus ket, and H, when it operates on this ket state, you will get E minus this minus ket state. Now actually we can do this address this Jaynes-state problem very easily if you recall what we learned in lecture 5 of module 1 in the context of two-level atoms. Just let me quickly remind you about that. Quick reminder about two-level atom. In semi-classical approximation we did that because there the atom was considered to be quantized. It has quantized energy level, and the electromagnetic field was considered to be classical, and there we got these results. If you recall the Hamiltonian, we wrote there, it was lecture 5, it was h cross 0 omega by 2. Omega is the Rabi frequency, and here you have minus delta. Delta is the detuning parameter, and the eigenvalues were E of this Hamiltonian we worked out as E plus minus is equal to minus h cross delta by 2 plus minus square root of h cross delta by 2 whole square plus h cross omega by 2 whole square. Okay, and the Jaynes-states we worked out as we defined it such that ket plus is equal to sine theta, the ground state of the atom, the ket state ket z, and it is cos theta ket e, while here we had minus ket is equal to cos theta ket z minus sine theta ket e. Okay, and with this angle theta is the Stackelberg angle, and that we worked out as tan 2 theta is equal to minus omega. Omega is the Rabi frequency divided by the detuning parameter. So this is what we have already learned in module 1. So in the similar spirit, then we can avoid doing detailed calculation. Let us take say Jaynes-state of the Jaynes-Cummings Hamiltonian to be, let me write it as sine theta. We have these two basis states, atom in the ground state, field n number of photons in the field mode, plus cos theta atom in the excited state, and there are n minus 1 number of photons in the field mode. To distinguish it from theta, let me just put a suffix n so that you understand that we are dealing with Jaynes-Cummings Hamiltonian or that system now, and your this other state is cos theta n, this particular state, minus sin theta n atom in the up state and n minus 1 photons in the field mode. Okay, so this is what we have. Again, without doing calculation, we can address this, we can find out this Stackelberg angle for theta here, because if you recall from lecture 16 that we have got the expression for the probability of finding the atom in the ground state at a instant of time say t as 1/2 into 1 plus cos of 2z square root of nt. And when we have started from the initial state at time t is equal to 0, the atom was assumed to be in the ground state and there are n number of photons in the field mode, then this expression we obtained in lecture 16. This shows that the Rabi frequency that we had in the context of two-level atom in lecture 5, here the Rabi frequency is for this completely quantized problem is 2z square root of n. Okay, so therefore we can now define the Stackelberg angle by this definition, that is tan 2 theta n is equal to minus the Rabi frequency here is 2z square root of n divided by delta. Delta is the detuning parameter, and this angle lies between 0 to pi by 2. Now let us work out this particular problem. You are asked to show that in the dispersive regime, that is when the magnitude of the detuning parameter is much larger than the coupling, the effective Hamiltonian for the Jaynes-Cummings model could be written in this particular form. Okay, so let us do it. In fact, we have discussed the dispersive regime of Jaynes-Cummings model in lecture number 16, and there, if you recall, we have written down the Hamiltonian, and in fact I request you to refer to that particular lecture number 16. There we wrote down the effective Hamiltonian in this form. It was h cross omega plus z square by delta sigma z a dagger a plus h cross omega atom plus z square by delta sigma z plus 1 by 2. Now various terms can be rearranged. So if we rearrange the terms, then we can write this effective Hamiltonian in this form. Let me take sigma z common. Then I have terms like h cross z square by delta a dagger a plus h cross by 2 omega atom plus z square by delta, and we have term h cross omega a dagger a plus half h cross omega atom plus z square by delta. This I can write little bit in a more cleaner form. I have sigma z h cross omega atom by 2 plus h cross z square by delta a dagger a plus half, and we have the other two terms h cross omega a dagger a plus h cross by 2 omega atom plus z square by delta. Okay, so in fact if you look at this Hamiltonian, this is what is asked in the question. This is the required form of the Hamiltonian, as you can see from here. Now let us interpret it. If you look at the first term, so this first term refers to the fact that there is transition between the two atomic energy level or the qubit energy level. We have two energy level. The excited one is h cross omega atom by 2 and the ground one is h cross minus h cross omega atom by 2, and they are separated by a frequency omega atom, or energy difference is h cross omega atom. In fact, you know that sigma z, the matrix form is 1 0 0 minus 1. So this clearly shows the significance of this particular term. And then let us look at the second term here. The second term, if you look at it, it is h cross z square by delta a dagger a plus half. So it consists of two terms, as if one term is just like in the harmonic oscillator. So this is basically due to the 0-point fluctuation. This particular term is, it has two parts. One is h cross z square by delta a dagger a dagger is the number of photons, and the other one is due to the 0-point fluctuation, that is half h cross z square by delta. Okay, now because of the fact that this particular term you have is proportional to the number of photons, and you can say that this term is analogous to the so-called AC Stark effect, because overall this whole term, it is related to the shift in the atomic transition frequency, and in the presence of the photons, that atomic transition frequency is basically getting shifted, and photons, you know, is related to the quanta of the electric field. So that's why we can term it as AC Stark effect. On the other hand, this term is shift, refers to the shift due to the vacuum fluctuation, and this has a name, and it is analogous to the so-called Lamb shift. On the other hand, this, you know that this is familiar to you, this is the energy of the field mode, and finally this term is there because it is needed to have our specific definition of 0-point energy. It is not related to any operator. This is related to simply no Pauli matrix, nothing is associated with it. This is just you can consider it to be kind of a offset term, and it is needed for our specific definition of 0-point energy. Let us now work out this particular problem. You are asked to show that the potential energy function of the transmon could be written in the form E is equal to minus Ej cosine of phi j minus phi 0. Phi j is the magnetic flux across the junction, and phi 0 is the so-called flux quantum, and Ej is the Josephson energy. In fact, we discussed about Transmon Hamiltonian in lecture number 18 of the course. There we derived the Hamiltonian for the Josephson junction in this form, Hj is equal to minus Ej cos phi cap, where phi is the phase difference across the junction. Let me give you a quick recap of the derivation. We started with the well-known expression for the tunneling energy in the Hamiltonian. So Hj is equal to minus Ej by 2 sum over n running from minus infinity to plus infinity, and we have this kth n plus 1, then kth n plus 1 and bra n. So this is the Hamiltonian we started with. This Hamiltonian can be rewritten in terms of phase difference across the junction phi, and which can be treated as an operator, and to do that we defined a new basis, that is phi basis, where this is defined as summation going from n is equal to minus infinity to plus infinity e to the power I n phi, and this is the kth n. Conversely, we can write this as kth n is equal to 1 by 2 pi integration 0 to 2 pi d phi e to the power minus I n phi phi. It's very easy to show it, that this is what you will get. This allows us to write the Hamiltonian in this form: Sj is equal to minus Ej by 2 1 by 2 pi integration 0 to 2 pi d phi e to the power I phi plus e to the power minus I phi, and we have this outer product. So this is, you can see this is an operator. So that's why what we can do, we can introduce a new operator, introducing an operator e to the power I phi cap, and that is equal to 1 by 2 pi 0 to 2 pi d phi e to the power I phi, this ket phi bra phi. So we therefore write Hj is equal to minus Ej by 2. You can easily write e to the power I phi cap plus e to the power minus I phi cap, and that is equal to minus Ej cos phi cap. So this phase difference phi is related to the magnetic flux via this equation that we discussed in our lecture 18. Phi dot is equal to 1 by h cross q into v, charge into v. Here charge is equal to the 2 electron charge 2e. So therefore we can write d phi dt is equal to, h cross is the reduced Planck's constant, that is h by 2 pi. So therefore I can write it as 2 pi by h. H is a Planck's constant, q is 2e, and v is the potential difference or voltage. And this I can write as 2 pi divided by phi 0 into v, where phi 0 is the so-called flux quantum, and it is equal to h by 2e. Now we can write, this phi of t is equal to 2 pi magnetic flux phi of t divided by the flux quantum, and where this magnetic flux phi of t is equal to integral of the voltage v of t dt dash. Okay, so therefore we can write the Hamiltonian minus Ej cos phi cap is equal to minus Ej cos phi cap is now it is operator. So we have 2 pi this flux phi cap by phi 0. This I can simply write as minus Ej cosine of magnetic flux operator divided by the flux quantum phi 0. And in fact this is the required energy function I have. In fact this is the part of the Hamiltonian, but again this is nothing but the energy function that we are asked to work out and solve.